So in section 3.10, we're going to look at something called the differential. And really a lot of what's going to go on is you're going to learn some more notation, and it's going to emphasize something that may or may not have been evident to you up till now, and that is the tangent line is actually a good approximation of the function near its point of tangency. I mean, if you look at this curve, so this curve is our function, the straight line is our tangent line, but when you're really close to the point of tangency, there's not a whole lot of daylight between the tangent line and the curve. In fact, in terms of the drawing, they blend. If you zoomed in enough and enough, you'd probably see a little bit of daylight, but you might have to zoom in an awful lot. So let's understand some notation here. We'll start out with, in fact, I'm going to call this point, say, x, not necessarily referring to the 2 there, and then move a little distance away over here, some x plus a little bit, which I'll call delta x. And let's look at the function at these 2 points. So if you look at the function at these 2 points, well, you've got this over here, which is f of x. And then at another point a little further down, you got this y height over here, and that's going to be your f of x plus delta x. Now the difference in that, we're going to call delta y. You may notice that I'm using this delta here. A lot of times I like to use an h, but here's one exception where I'm going to use the delta. Delta means change in. So to go from here to here, that's a distance of delta x. In the same fashion, in going from this y value to this y value, the difference in those is going to be my delta y. And delta y is going to be defined as it is down here as the difference in these 2 heights. So it's going to be f of x plus delta x minus f of x. That's your delta y. So why am I messing with this? Well, we're going to try and build some approximations, help you understand a little bit more about tangent lines. So let's take a look at this equation right here. Delta y is f of x plus delta x minus f of x. I can rearrange that a little bit, and let me just do that up here. I'm going to move things around. F of x plus delta x, so I'll keep that by itself, is going to be delta y plus f of x. So it's your original function plus a little bit of a change is what you're getting. We'll just kind of put that off to the side for the moment and focus in on the tangent line for a bit. Now if this is my function y equals f of x, then the tangent line is right here. How do we find the slope of the tangent line? Say again? The derivative, right? So the slope of the tangent lines can be measured by the derivative. So, okay. Now, let's see. If we have y equals f of x, then dy by dx equals f prime of x. I mean, that's what we've been doing all along in chapter 3 with our calculus, is we've been differentiating these things. But this notation, due to Leibniz, has some other benefits. I can regard this delta x as being the same as dx. I'm going to define these things independently. And that allows me to multiply both sides of this equation by dx and get dy as f prime of x dx. So now I got an explicit expression for that numerator term. Here we can start seeing the genius of Leibniz notation here, because it allows this kind of interpretation of the slope of a tangent line. The differential of a function is going to be dy equals f prime of x times dx. Now what's that going to turn out to be? Well, this is going to be the change in the tangent line, or the slope of the tangent line times its change. And so what it turns out to be is that dy is not the change in the function, which is what delta y is. Dy is the change in the slope of the, or change in the tangent line. So this is your dy term right here. This part right here, that's dy. dy is the change in the tangent line, whereas delta y is the exact change in the function. So change in the tangent line Well, why is that important? Well, it's going to give us a different way to approximate the value of a function and show you also that the tangent line is useful for some things, mainly being approximating a function. Let's look back at this equation. I have f of x plus delta x. So my function evaluated at some new point is the function evaluated at the old point plus the exact change in the function. That's fine. But I want to tweak that a little bit. I'm going to tweak it this way. I want us to notice that the exact change, which is my delta y, the exact change in the function is going to be pretty close to the change in the tangent line as long as delta x is really small. That is, if I'm not changing what point I'm looking at too much, if I'm moving just a little bit, these two things are going to be close to each other. So for small values of delta x, not delta y, for small values of delta x, dy is approximately delta y. And that means that delta y can be approximated by dx times, or f prime of x times dx. So delta y is approximately f prime of x times dx. Because that's what dy is. dy, we just derived it up here, is f prime of x times dx. That's actually one of the conclusions that I want for you here. There's several conclusions, so let's start filling in some of these conclusions. The first one is that delta x and dx are interchangeable. They mean exactly the same thing. The second one is that delta y, the exact change in the function, or excuse me, delta y, the exact change in the function is approximately dy. That's exactly what this is saying. Delta y being your exact change in the function, dy being the approximate change in the function. Now, one thing that this leads to is a couple simple problems on an exam. But there's simple problems that people tend to get wrong. And let me explain why. Let me do kind of a quick example. Right here. Let's do two quick examples. So example, I don't know. is going to throw off my, I'll call it double A, example double A. Y equals sine of x to the third, and y equals, let's see, tangent inverse of x. And the instructions would be find dy. Okay, not bad. But to find dy, really we need the derivative, right? dy is f prime of x times dx. Okay, great. So we'll start by calculating dy by dx. And by now you guys are experts in the chain rule, so let's just grind this out, right? It's going to be derivative of the outside, which is cosine, of the inside, times derivative of the inside, which is 3x squared. But if you put this answer into WebAssign or on an exam, on WebAssign it'd be completely wrong. On the exam you'd lose a point of 2, maybe 2, because it's asking you to find dy. Now the nice thing is that we've done all the hard work. To find dy, the change in the tangent line, you're just going to multiply both sides by dx. dy is going to be 3x squared cosine of x cubed dx. And that's it. So the only layer that you're adding is just figuring out or multiplying both sides by dx when you're all done. So that you get f prime of x times dx. That's the differential. That's your dy. Let's do that again with this one over here. dy by dx. It's not something that I use very much in a Calc 1 semester, but it's going to become more important in Calc 2. So hopefully you at least have the derivatives memorized. Derivative of the inverse tangent is going to be 1 over 1 plus x squared. But here again, you've got dy by dx. If you're asked to solve for dy, then you need to multiply both sides of this by dx and end up with dy equals 1 over 1 plus x squared times dx. So this last step here is that you're really multiplying both sides of the equation by dx. On the left hand side it cancels, on the right hand side you get this. So let's see what good that does us. I'm going to try and put things into perspective with the back side of your handout. First thing I want you to do is I want you to figure out that if we're working with the equation y equals the square root of x, that's our equation. What's dy? And I've kind of given you part of this. I already gave you the derivative of y with respect to x is 1/2 x to the negative 1/2, or 1 over 2 square roots of x. What's dy going to equal?
One over 2 square root of x dx.
Yeah, just multiply both sides by dx. Thank you. 1 over 2 times the square root of x times dx. Beautiful. That's all you're looking at. Now, that expression I can type in down here. Let me rewrite it as maybe dx over 2 times the square root of x. And the point of the derivative and the tangent line said, or one thing that you can do with the tangent line is realize that the derivative is a good approximation of the function at that point of tangency. So if you're looking at, for instance, the the square root function. Y equals the square root of x. Then the graph is going to start at the origin. It's going to look like half of a sideways parabola. Something like that. So you got x equal 1. But the tangent line is a good estimate of our square root function. And as long as we're close to the point of tangency, say x equal 1, then we should get a close estimate. So what if we look at a nearby point? Say at x equal 2. And let me make it 2 or 1.5. The farther I move away from my point of tangency at the point 1, 1, the worse that this tangent line is going to be in approximating the value of the function. But as we get closer, say to 0.5 or to 0.1, 1.1, as we get closer to this point of tangency, the tangent line is going to be a better and better approximation to this function. Now let's see what happens here. If I wanted to use the tangent line to look at x equal 2, well, I know the exact value of the function at 2. The exact value is the square root of 2. The difference between my new value and my old value is just square root of 2 minus 1, which is 0.4 something. But I want to look at things with the differential. What's going to happen with y or dy? To get dy, I need two things. I need to know what delta x is, or dx. I need dx and x. And I've got both of those. Those are right here. So let's fill in both of those pieces. X is my original point of tangency. And remind you, delta x and dx are the same thing. So this is dx equals delta x. Those are interchangeable. If I put those things in, I'll end up with 1 for delta x over 2 times the square root of 1. 1 over 2 times the square root of 1 is 1/2. So while the exact change in the function was 0.4, my estimate of that change is 1/2. Well, not so great. Not terrible, but not great. What if we made this closer? What if we made this my delta x right here? So delta x, which is dx, is 0.5. Now how does that change things? Well, I put in a 0.5 for my delta x divided by 2 over the square root of 1, and now I get 0.25. And, you know, that's a better estimate of the change, the exact change in the function. The exact change in the function is 0.2247. Yeah, that's better. And it's going to keep on getting better as you decrease this interval. So let's do the last one. If I bring things down to this point right in here, 1.01, how good is my tangent line going to do? Well, 1 plus 0.01 is going to be 1.01. This is going to be the square root of 1.01. What am I going to fill in right here? How am I going to get the exact change in the function? Square root of 1.01 minus 1. And calculator to do that part. Square root of 1.01 minus 1. Should be pretty small. 0.00498. Let's check out what the change in the tangent line is. How does the approximate change in the tangent line compare to that? Well, let's fill in that value here. What I need to do is I need to plug in delta x divided by 2 times the square root of x. X in our case is still 1. That's our point of tangency. Delta x was 0.01. So it's going to be 0.01 divided by 2 times the square root of 1, which is going to be 0.005. So this is the exact change. Here's our approximate change. Are those pretty close? .00498 and .005. Are those pretty close? Yeah, I think they're remarkably close. So, as I said, as this interval decreases, as delta x gets smaller and smaller, and you're looking at the function at closer and closer points to the point of tangency, your tangent line is going to be a better and better approximation to your the change in the function. So, all right, let's actually do some problems that you'll see as you go through the homework. It's kind of a lot of stuff there to wade through. So the first two are going to be kind of more of the friendly variety. So example A is y equals 1 over x cubed minus 4x. And the goal is to find dy. Now, of course, that's going to mean you have to differentiate. And when we differentiate this one, what comes to your mind? Quotient rule? Sure, nothing wrong with quotient rule. Does anything else come to anyone's mind?
You can put it to a negative power and use the chain rule.
Yeah, you can put it to a negative power and use the chain rule. Let's try both. dy by dx. First I'll do the quotient rule. It's going to be x cubed minus 4x squared. So the denominator, and then the denominator times the derivative of the numerator. Somebody help me with the derivative of the numerator. Dean, thanks for volunteering. What's the derivative of the numerator going to be?
The numerator?
Derivative of the numerator, yeah.
1.
The 1. What's the derivative of 1?
0.
0. Yeah, 0. Yay. Minus the numerator times the derivative of the denominator. Awesome. So, what's the derivative of the denominator?
3x squared.
Adrian?
3x squared minus 4.
Awesome, thank you. 3x squared minus 4. So overall, that's going to be minus 3x squared minus 4 over x cubed minus 4x squared. Beautiful. Let's try it a different way. Or, somebody suggested, I think, Kyrillos, you suggested writing it like this. Maybe it was it Kane? One of you.
That was gross.
Okay. Writing it like this. And now when we differentiate this, dy by dx, it's It's going to derivative of the outside, x cubed minus 4x to the negative second times the derivative of the inside, which is going to be your 3x squared minus 4. This part, and only this part, can go down to the denominator. I'll leave the negative up front, minus 3x squared minus 4 over x cubed minus 4x squared. So you get the same thing either way you differentiate it. It's just a matter of preference, and do you see it on the fly? But either way, this answer is not getting you 100%. In fact, on the website, it'd just be wrong.
You know, the d of x.
Yeah, you gotta multiply by that dx. So really, in my opinion, this is just kind of like a fancy way of figuring out, do you know how do you differentiate? Because I mean, multiplying by the dx is not a big deal. So dy is gonna be negative 3x squared minus 4 over x cubed minus 4x squared dx. You need that dx here to get these problems right. Sorry, it's just the way it is. Let's try another one. Let's see.
D.
So example B. Y equals the square root of 3 plus cosine of theta. And again, you're gonna have to find the differential. So it's gonna be find dy. Probably something you're gonna need to do before you do this problem, before you really get busy on this problem, I should say. What is it? Yeah, you're gonna have to write this as something to the 1/2 power. William?
For the question, it says find the differential of the function. On the test, will it say find dy or?
I could do either.
To assume,
I could do either.
okay,
The differential is gonna be, yeah, just the numerator part of what we usually write as a derivative. For instance, when we differentiate this, my first thing is going to be dy d theta, because theta is the dependent variable on this, or independent variable. So I'm going to differentiate with respect to theta. But when you find the differential, it's just going to be the numerator part of this, whatever variables you have. 3 plus cosine of theta to the negative 1/2. Daniel, what's the derivative of the inside?
Negative sine theta.
Negative sine theta. Please be careful. If you write this like this, make sure you use parentheses here. So that's this times this. Writing it without parentheses, it looks like you're subtracting those two. And, you know, it's a problem that I grapple with, like, all right, well, how do I want to grade that? Because I know what you meant, but it's not what's written. If you type that into your graphing calculator without parentheses, it would subtract them. So be careful, because instead of getting it necessarily right, then you're subject to, if I've been having a good day when I grade your exams. So, all right, I'm kidding a little bit on that one. I try and be more objective than that, but there we go. We're still not done. What's wrong with this? Yeah, I need to get rid of that denominator part there. So I'm going to multiply both sides by d theta. And it just means tacking it on at the end. That's all it is.
Yeah, I said dx, it's d.
And d theta. I knew what you meant. I knew what you meant.
Don't wanna do it on an exam either.
Yeah, so on the exams, I'll just grade you on what you meant, right? Yeah. I meant to have it right there. Yeah. Example C. Let's finally go a little bit farther than what we've been doing. Let me remind you of when you differentiate e to some power, it's e to that power again times the derivative of the exponent. So that's the one we need here. In our case, it's e to the x over 2. You might also want to write that as e to the 1/2 x. That way, hopefully you won't be tempted to use the quotient rule when you differentiate this. It's just derivative of a constant times x. So go ahead and try and race me. Write down what the derivative with respect to x is going to be. While you play with that, let me play with decimals for just a second. Okay. So the derivative here is just going to be the function itself, which is e to the 1/2 x times the derivative of the exponent. What's the derivative of 1/2 x? 1/2. Now, maybe I want to rewrite that a little bit as, let's see, do we want to put the 1/2 out in front? We'll do e to the 1/2 x over 2. And finally, hopefully you finished up with this last step, right? This is the important step that gets you all the points. Multiply by dx. All right, so there we go. That's your part A. Now there's a part B on this as well. So let's continue with part B. So that's part A. Part B says, all right, well, if x is 0 and delta x or dx is 0.05, find dy. dy. Well, that's going to mean plugging in these values in for x and dx respectively. There's going to be e to the 1/2 times 0 over 2 times 0.05. So 0 here for x, 0.05 here for dx. So that's going to be e to the 0 is 1/2, or e to the 0 is 1, divided by 2 is 1/2, times 0.05. I don't think we need a calculator for that. That's going to be 0.025. So that's your value of dy. And that's all that they asked for here. So let me try and put this into some context. And that would be here. So you're looking at the function at some point at 0 and 1. And you want to compare what's happening with the function at a point that's close by. 0 and, 0.05 and 0.05 and 0. So you're looking at the function at these 2 points. Now let me zoom in drastically. The difference in these two values, f of 0 or f of 0.05 minus f of 1, that's the exact change in the function. That's the distance along the y-axis. What we're getting in looking at dy is the approximate change in the function as measured by the tangent line. So the exact change in the function was 0.0253. That's when you look at the difference in the y heights. If we did this for the tangent line, and the tangent line here I think is line y equals x plus 1. No, that can't be it. No. Oh, 0.5 x plus 1. Let's try that. Yeah. If you look at the difference in the tangent line's pretty close there. The difference in the tangent line was 0.025. So we got a really close answer there. All right. I've got time for one more. So let's choose example E. Just kind of move on in a linear direction. Caitlin?
No, it's okay, I can ask afterwards.
I
was looking at example D's here.
Okay. All right, so you're asked to find a linear approximation of the function cube root of 1 plus x at x equals 0. They put a equals 0. I think it was x equals 0. And then use that approximation to find some other values. So, okay, let's see if we can't do that. It's going to start basically by finding the equation of a tangent line to this function at x equals 0. So let's do that part. So my function is g of x equals the cube root of 1 plus x. And I want to find the equation of the tangent line at x equals 0. So let me first do this. Let's find the coordinates of this point. Find the coordinates of where the tangent line is going to be by plugging in x equals 0. So g of 0 equals 1. So 0, 1 is your point. That's your x1, y1. And now I need a slope. What's the slope of the line going to be? How am I going to find the slope of a line? Plug what in?
0.
Plug in 0 to the derivative. So first we need the derivative. So g of x, probably want to rewrite that as 1 plus x to what power? 1/3 power. So the derivative is going to be g prime of x equals 1/3 times 1 plus x to the negative 2/3, or 1 over 3 times 1 plus x to the 2/3. Okay. M tan is going to be G prime at 0. And if I plug in a 0, the slope of the tangent line is what? Slope of the tangent line is 1/3. All right, so that's our M tan. Let's find the equation of the tangent line. So y minus y1 equals m times x minus x1. We've got our point, which is 0, 1, and our slope, which is 1/3. So y minus 1 equals 1/3 times x minus 0. So there's the equation of your tangent line. But here's an important part. You're not going to be able to get this problem right off your calculator. You're asked to approximate the cube root of 0.95 and the cube root of 1.1 using your linear approximation, which is this. Now, we're going to have to do a little bit of thinking here. If I'm going to approximate 0.95, what does that mean x was? If you compare this to this, negative 0.05. So, cube root of 0.95 is going to be approximately, that means x is negative 0.05. Negative 1/3, or excuse me, 1/3 times negative 0.05 plus 1. I mean, that much you can do on your calculator. So negative 0.05 divided by 3 plus 1 is 0.9833. And they ask you to round it to 3 decimal places. 0.983. How about the other one? The last part of this problem and the last part of this section. This time we want to approximate the cube root of 1.1. So, all right, let's do that. So for the cube root of 1.1, 1.1, now I need to figure out what x is again. Keep in mind that what's underneath the radical comes from 1 plus x. So 1 plus x equals 1.1. What does x equal here? 0.1. So my approximation then is going to be 1/3 times 0.1 plus 1. You can again take out of your calculator. You should get 1.033333, but rounding it to the nearest third decimal digit gives you 1.03. But these last couple types of problems, you have to come up with the equation of a tangent line and then use the proper value of x to figure out what your equation is.